Hello and welcome everybody. We are so pleased to welcome you into this session with Leidos today. I believe that you're all joining from a YouTube stream, so I just wanted to let you know that during the session you'll be able to use Menti, and if you look on the screen there, we've got a Menti QR code, and there's also a little code you can type in if you're using a browser and you want to go to menti.com. So please get ready to interact with us throughout the session today. We will just bring you forward onto our slides. There we go. So my name is Fiona Keady. I work in a company called Leidos. The name actually comes from the middle of the word kaleidoscope. Leidos is a massive technology, science and engineering company. We have about 47,000 people working for us worldwide, so a really big company. There's about 1,200 of us in the UK, and there's just 5 of us here to speak to you today. Some of the work that we do in Leidos is all about planes and keeping planes safely in the sky. So the session today is going to look at things like how do planes actually stay in the sky? Why do we need to manage all the air traffic and stop planes from crashing into each other? How can artificial intelligence help with some of this as well? And as I mentioned, we've got lots of interaction throughout the session on Menti as well. So make sure you're paying attention as we go through. I mentioned that we've got some of our Leidos co-workers here with us today, so we're just going to bring them in one by one so they can meet you. First one is Dan. Dan, do you want to come on camera?
Hi everyone, my name is Daniel Barber. I'm joining from Southampton, so I'm on the south coast, and I've been worked for Leidos for around 10 to 11 years now. And currently I work on a program called Intelligent Approach, which is a piece of software which is currently live and operational and keeping planes safe at London Heathrow Airport, so one of the main airports in London. And as part of that project, my role is as an engineering lead. What does that mean? It means I try and keep the project on time, so on schedule, on budget, making sure we look after the costs, and also providing technical support, trying to answer some of those really hard engineering questions or some of those challenges that come up. Interesting fact about myself, I got into engineering mainly because of my brother. My brother's a little bit older than me. He went off to university and did an aerospace engineering degree, which is basically a degree all focused about all of the kind of science and physics and maths associated with a plane. And yeah, I spoke to him and I thought, wow, that sounds really interesting. It's something that I wanted to get into.
Fantastic. Thank you, Dan. And next up, we have Mike.
Hey everyone, my name's Mike Lamb. I work with Dan as well on the Intelligent Approach project. I've worked on the Intelligent Approach project for about 4 years now. I've been with Leidos for about 7 years. And yeah, my role is as a test lead on the Intelligent Approach program. So that means I'm responsible for making sure that the software that we create actually does what we think it does. So, you know, mistakes happen everywhere at all points. Everyone makes mistakes. And my job is to try and minimize the amount of mistakes that actually come through. So making sure that software is as safe as possible is really the kind of main kind of focus of my role. And yeah, an interesting fact, in my spare time, I like to DJ. I also do my own radio show.
Wow, so you'll be used to all of this then, Mike.
Yeah, no problem.
Great. Thank you, Mike. Next, we have Lewis.
Hi, everyone. My name's Lewis Woods. I've only been at Leidos for 3 weeks, so I'm very new. I work with both Mike and Dan as well on Intelligent Approach. And my job is as a software engineer. What does that mean? Basically, I write sets of instructions for computers so they can basically carry out the Intelligent Approach software. And involved in that is testing and making sure the software runs correctly, because we want it to be mistake-free, as Mike was alluding to there. Fun fact about myself, I've recently started scuba diving, and I also enjoy rock climbing.
Nice. Thanks, Lewis. I didn't know you had those hobbies, or that you'd only been here for 3 weeks, so it's very, very new to join. We have Yadola next. Oh, you're just on mute there, Yadola.
I'm on mute, sorry.
Okay.
Yeah, my name is Yadola Mustafi. I joined Leidos about 2 months ago, just over 2 months ago, as an engineer manager, looking after intelligent approach, like Dan and Mike and Lewis. What does my role means? It sort of make sure that we talk to our customer and my colleague to facilitate and make sure that the software or the system we design are to the cost, time and schedule. But we also make sure that the development team, they got all the tools and everything that they need to use. Interesting fact, perhaps we need to go back to the dark ages when there was no mobile phone in the UK, and I work on the first mobile exchanges in the UK to bring what you use it as everyday item. And I also part of the team that developed and delivered bomb disposal robot for the UK MOD.
Wow. Very important work there, Yadola. Thank you for sharing that.
That's okay, thanks.
I don't know how to follow that up now. So yeah, I'm Fiona Cady. I've worked at Leidos for about 7.5 years now. I work in the talent development team, which is all about learning and inclusion and helping people to have fun at work as well. So quite a nice job for me to have. I lead our STEM employer resource group as well alongside Dan. So we get to do lots of work with school pupils and at colleges and unis as well. So if you have any questions around any of that, then please feel free to submit them later on in the session. But we just want to welcome you all today. My fun fact, I suppose, would be that I'm learning British Sign Language. So that's something that we feel really strongly about in Leidos and trying to make sure everything's accessible to everybody. So I'll try and put some sign language in wherever possible. So that's our team for today. Thank you for being with us. We'll just move us forward. We're going to go into our first Menti question. So the first question is, where are you? This could be the city or town that you're in, or if you're in school or at home. We've got the Menti code there again. So just as before, if you use your QR code or go to menti.com and type in that code. So the code is 8851 1804. And we'll just give that a wee minute or two. And I think Jamie and the team are going to read out some of the answers potentially. So I can see some coming through now. So we've got Scotland, Longridge, Moss Head as well. Fantastic. I think even in Leidos, I'm based up in Glasgow, and Dan and maybe some of the others are based down in Southampton, Whiteley sort of direction. So we're quite well spread as well across the UK.
Yeah, so in our team, we've got about 30 people and we truly are spread throughout the UK. So as you said, quite a few people in Southampton, quite a few people in around Glasgow and Edinburgh. So we've got a big office in Glasgow, Sky Park, the Sky Park offices that you may know there. But then we've got people down in Devon and Cornwall and people up in Dundee and people in Coventry. So yeah, all over.
I'm glad you mentioned Coventry.
Is that where you're based, Yadola?
Yes, I've been
Yeah.
sent to Coventry.
Oh no. Oh, well, thank you for dialing in from there.
It's all right.
I can see there's a Westerton as well in the chat there, and also Lewis thinks he's the furthest north in Dundee, so I don't know if anybody could challenge that answer. But Jamie and the team, if you just let us know whenever we are finished with this one, we can move on to the next one. Let's move on. Okie doke. So we will move on to our next one. I think that's all the answers for now. So our next question is, what age are you? I know we have some teachers dialing in as well, so if you want to put in young at heart or something, then feel free to do that. But we were just interested to know what sort of age everybody is that's dialing in today. Again, I'll just give this a wee minute or two so we can see what pops through. Anybody who's just joined, and we're doing all of this on Menti, so menti.com with the little code there on screen, or you could use the QR code in the corner. Mike saying he feels about 60. Yeah, I can share your pain, Mike. Oh, so we've got 3 votes for 11, 1 vote for 10, and 1 vote for 12 so far. So all fairly similar ages. I guess round about top end of primary school, start of secondary school, so that's a good mix there. So I think we've got quite a lot of content to go through today, so I'll maybe just move us on from this one just now, but we will be using Menti again later in the session. We're going to go on now to have a look at how planes stay in the sky. And we're going to go over to Dan for this part and explain some of this. And then please try and keep this in mind, because we've got a little, almost like a voting competition thing after this, haven't we, Dan? So I'll leave it with you.
Yeah, no, definitely. Thank you. So I know when I was kind of your age, I would love going to the airport. So I grew up in Chester, which is kind of near the Midlands. So I used to go to kind of Manchester Airport and watch the planes take off and land there. And I always was so fascinated about kind of how did they actually fly. And it wasn't until kind of much later on at school and then later at university that kind of figured out, oh, that's how they actually fly, how they actually stay in the sky and basically take us on holiday or take us wherever we need to be. So I thought we'd just share a little bit of information here about how the planes actually stay in the sky. And essentially, there are 4 main forces which are kind of acting on the aircraft, and they act in pairs. So you have lift and weight acting and almost fighting against each other. And then you have thrust and drag. Again, they're kind of almost fighting out, and whichever one is kind of the biggest force means that one's winning. So if lift is the bigger than weight, that means the plane will climb, or if thrust is bigger than drag, that means that the plane would accelerate, and or the other way around. So if drag is bigger than thrust, that means the plane will slow down. But when we're kind of going on holiday and we're just cruising through the sky, one of the really interesting things is that all of these 4 forces are kind of equal, or what word we might use is they are in equilibrium, which just means that they're all equal. So I guess kind of one of the questions is, what do we even mean by lift, thrust, weight, and drag? So what we're going to do on this slide is just take a few moments just to go through what these terms mean, and just try and build up that kind of mental image of what they do mean. So I don't know if Mike, you want to go first with thrust?
Yeah, of course. Thanks, Dan. So yeah, as the slide says, so thrust is the force that's actually kind of propel the aircraft forward. If you've ever been on a flight, you'll have actually experienced this. You'll have felt that. One of my kind of favorite things when I'm going on a holiday and you're getting on your plane and you're strapped in and you're getting ready for takeoff and you hear the engines kick in and all of a sudden the plane starts to move forward, and as soon as it really kind of picks up speed, you're getting chucked back in your seat and you're getting pressed back, and that's because of the thrust behind you acting on your body. So yeah, you can actually feel and you can experience that when you're in the aircraft. So yeah, that's my analogy for thrust. Who's
Thanks,
next
Mike.
up? Thanks, Dan.
Yeah, so I'll go next, because so Mike is there pushing the plane forward, and then I'm going to start talking about drag. So kind of me and Mike are kind of acting opposite each other. So what is drag? So as Mike said, he's the thrust, he's the propulsion, he's pushing the aircraft forwards, but the aircraft's being pushed forward into wind, into air particles. We can't see them, but we know them. They are there. For example, if we're running along and we can feel the breeze in our face, that's kind of the air particles. And as we move through the air, basically the aircraft needs to move those air particles out of the way so the plane can kind of take off and fly. And so what drag is the force of or the act of moving those air particles out of the way that creates what we call drag, and that's called the proper term for that is friction drag, and that's one of the main elements of drag that is created in terms of an aircraft. The other part is called induced drag, very kind of scary sounding name, but it's quite straightforward. So in terms of the wing, we have airflow going above the wing and airflow coming below the wing, and those two different airflows, those two different parts of air have different characteristics, they have different behaviors, and then when those two merge, when those two mix at the tail end of the plane, that creates kind of turbulence. It creates what we would call wake turbulence, and that creates drag as well. So in that kind of competition between kind of thrust, which was Mike, and me as drag, when the plane's taking off, Mike is definitely winning as thrust. But then, for example, when we're slowing down and coming into land, for example, then drag will be bigger than thrust, and I would be kind of beating Mike in that analogy. But yeah, next we can go to Udola, who I think is going to be talking about lift.
Oh, thanks, Dan. Yeah, as Dan said, the air particles moving, and the shape of the wings are made such that the air above the wings are moving faster, sorry. It's moving faster, and that moving faster means lesser pressure on the wings and than what is coming from the below the wings, and that the delta in the forces, two forces that we have, the air at the top and the air at the bottom, that delta force is what causes the lift, which is one of the forces working against the weight. And now we go to Luis.
Thanks, Udola. So as Udola mentioned there at the end, lift is acting against weight. So what is the force of weight? Basically, the force of weight is the force caused by the gravity of the Earth, which pulls the plane down towards the Earth. If you've ever watched maybe like footage of the moon landing, you'll know that the astronauts were sort of floating around on the moon. That's because the moon is smaller than the Earth. So depending on which body in space we're on or close to, the active or the force of weight is greater. So to counteract the force of weight, the lift obviously needs to be greater than weight. If you've ever gone on holiday and you've had to check in luggage when you've gone on a plane, you'll know that there's like a weight limit, because the force of weight is also influenced by the mass of the objects that the gravity is acting on. So for example, say we have a plane with 200 people in it, that's going to have a smaller weight acting on it than a plane with 500 people. Same with how much luggage is in the plane as well.
Perfect, thank you, Lewis. And so as Udola and Lewis were saying, the weight and the lift, they're kind of having that competition as well, and depending on which force is bigger depends if it goes up and down. And so we're going to move on to kind of another slide which talks about paper airplanes. But yeah, just when we move on to this slide, just keep those forces in mind, because they might help you out in the next few slides.
Good tips, Dan. Thank you all for your explanations. So as Dan mentioned there, we're going to ask you our next Menti question, which is, can you guess which plane flew the furthest? So we've made these 5 paper aeroplanes. We've got a video to show you of what happened with them all, but we wonder if you can guess which one is going to fly the furthest. So the options here, the first plane is called the Basic. The second plane is called the Dart. The third plane is the water plane. The fourth one is the buzz. And then the fifth plane is the underside plane. So again, if you could just use Menti to put your votes in just now, and we'll see what comes through. If you need it, the code for Menti again is 88511804. So that's the Menti code 88511804, and that's on menti.com. So we'll just give you a wee minute or two to have a think about that. As Dan mentioned, think about the forces that we talked about. You might want to look at the size or the shape of the wings. Maybe you're just picking your favorite color. We don't know. But just choose whichever one you think flew the furthest. And then we'll see what the votes tally up. And then we'll show you the video of what happened. Looks like we've got 3 votes so far for 5. So the underside plane, quite popular one. Also 3 votes for number 4, which is the buzz. So these 2 are quite popular just now.
I'm going to vote for number 5 as well, I think.
Oh, is that Mike? Yeah, Mike, vote for number 5. Oh, excellent. Oh, we've got a vote for number 2 coming in as well, the Dart. Any of our other Leidos people want to put a vote in? I know, Mike, you've gone for 5, the underside plane.
Yeah, I think I'll go for number 1 because I like the colour blue and I think the colour might have something to do with it.
Good a reason as any. So Dan's going for number 1, the Basic.
I think I'll go with the audience and say the Dart as well.
The Dart as well. Yeah, good choice. So we've got a good spread of all of these. I don't know if I've seen any for number 3, the water plane. So well, let's click onto the video now, I think, and we can see how all the planes got on. No votes for 3. That's a shame. I'll vote for 3. I feel sorry for it. So I will just play this. Hopefully you should be able to see this, and there's some sound as well, but we do have captions just in case. So let's see if we can get, oh no. There we go. That should be us now, hopefully. Oh no. Jen, I don't know if you're able to help out with this at the video part. Thank you.
We folded and flew 5 different paper aeroplanes, but can you guess which one flew the furthest? First up, we have the Basic.
Uh-oh.
Then we have the Dart. Next up, the water plane. Followed by the buzz. And finally, the underside plane. Did you guess it correctly? The winner was the Dart. Thanks for watching and see you soon.
Thank you, everyone, and sorry for the technical issues there. We will now be able to move on to the next slide and see what the results are. You'll have heard there that the Dart was the winning plane, so let's just see if we can move on. Lovely. We're going to go over to Mike for a bit of a chat about why that might have been the one that won.
Thanks, Fiona. So yeah, this is kind of quite interesting, and this is kind of what this is kind of like what my job is in terms of testing. A lot of testing is taking information that you already know and then making predictions based on that information. And I decided, I thought the red plane was maybe going to be the one that would fly the best. And I thought that because it's got some nice big wings, and airplanes need big wings. So that was kind of why I chose that. It came in second, so not a bad guess. But yeah, there's some kind of different attributes that some of these aircraft or these paper planes have that make them, that have kind of helped or hindered them. So number one, there's a few things that kind of stand out there actually about why that might have been the best airplane. It looks like it's really aerodynamic, and if something's really aerodynamic, that actually means it creates less drag. So that's going to help propel it further than the rest of them. The red plane, however, that's got bigger wings, and that's going to give that better lift as well. And that's why that one's came in quite well. If we look at the third one, much narrower, not quite as slim and angular as the first place plane. So again, not as good aerodynamics and not as wide a wingspan as well. So it's not performed quite as well as the first or second flights. The fourth flight, it's a bit of a strange one, that one. Strange layout, strange colors, a lot of things going against it. And then the fifth one, well, that's the one that Dan picked. So of course it came last. But this is quite a kind of important or kind of useful thing to think about from a testing point of view, is that we're always open to new information. And as we find out new information, we then adjust our own thinking to account for that as well. So quite often with software testing, you repeat tests over and over again, taking into account new information that you receive, and it allows you to make better predictions. Now, don't worry too much if your guess didn't win, because making predictions is quite tough. And one of the other things that you've got to be aware of as a tester is, did the test itself have any influence on the outcome? So, Fiona very kindly went and flew all those airplanes for the demonstration, but maybe she was cheating a bit. Maybe she wanted number one to win, and she gave that a really good throw. I'm just saying, these are maybe you had a vested interest, Fiona. So that's kind of something as testers we always want to be aware of as well. Is there anything that we're doing that's actually influencing the outcome of the test, and to be aware of that bias and to try and correct for it in our testing as well.
Lovely. Thanks, Mike.
Oh, yeah, back to you, Fiona. Thank you.
Lovely, thank you. So great explanation there, and hopefully you're not too disappointed if your plane didn't come first there. We are now going to move on to our next slide, which is looking at planes that have changed over time. So we're going to go back to Dan for this part, who's going to chat through. And I think we have got a Menti question again. So once Dan's finished explaining some things, then we can maybe pop that in as well, but try and think about what's similar and different. Over to you, Dan.
Yeah, cheers, Fiona. And as we've kind of heard, we've been talking about kind of the forces which act on a plane, and then we heard Mike talking about some of the different aerodynamics, the different shapes of the wings that might increase lift or reduce drag. So when we're kind of looking at these two different aircraft here, use what you've learned already today to possibly think about those similarities but those differences, or anything else that comes into mind. So we've got two aircraft here. What are they? Why are they important? So that first one there, the Wright Flyer, so that was the first ever powered aircraft in the world. So this was created by a pair of brothers in the United States. So the Wright brothers, you might have heard. And they were a team of engineers, and they thought that they could build an aircraft, a powered aircraft. So we'd had hot air balloons for a long while. But with hot air balloons, you're very much at the mercy or of the wind. So the wind, whichever direction the wind's blowing, that's the direction that that you want that you will go. But with planes, that gives you the power of if you want to go from one place to a destination, it gives you that kind of power and control there. So, yep, in 1903, in a place called Kitty Hawk in America, they flew and they flew for 30 meters, which is, not very long at all. And the flight lasted only about 10 or 20 seconds. And then the fact that always fascinates me, you might have seen or you heard Lewis talking about those moon landings when those big rockets went over to the moon. The thing that always amazes me, we went from not being able to fly an aircraft to landing on the moon, and the time scale within that was only about 60 years, which still kind of blows my mind. And then the picture on the right hand side, so that's a modern aircraft. So you might hear names like Airbus and Boeing. They're the two main manufacturers of aircraft. So when you're going on holiday, it'll probably be an Airbus aircraft or a Boeing aircraft. And we talked a little bit there about the history of aviation. So we started flying in 1903, and in those first 20 years, we were just doing something called trial and error, where engineers would think, oh, would it be better if we did this or did that? And it was all quite dangerous. And then it was around the 1920s where people really started to truly understand what made a good aircraft, what made a bad aircraft. And that continued to advance through the 1940s. And then about the 1940s, 1950s, there were actually quite a lot of planes flying, and it was all getting quite busy. And it was at this point where we realized we probably need someone to coordinate and talk to all of the different aircraft to make sure there won't be any kind of crashes, any mid-air collisions. And that's when we start looking at the idea of air traffic controllers. So these are the people who talk to the pilots, basically tell the pilots where they should fly, where they shouldn't fly, and it's their job, as I said, to get everyone, including the plane, safely from point A to point B. So in terms of here in the UK, we've got a number of different air traffic controllers. So you might see, when you go to the airport, you've got the air traffic control tower, that really tall building by the runway, and they look after all of the aircraft whilst they're at the airport. But as the aircraft take off and flying over the UK, there's two what we call air traffic control centres in the UK, and they look after all the aircraft which are flying above the UK. There's two, as I was saying, one in Southampton, and that basically looks after all of the planes flying above England. And then there's one in Prestwick, which is about an hour's drive away from Glasgow, and that looks after all of the planes flying over Scotland. But it also looks after a lot of the planes flying over the Atlantic Ocean. So all of those aircraft going to America and Canada, all of those are controlled out of Prestwick. And at any one time, there's about 100 air traffic controllers in the UK, making sure that we all get to our destinations safely. So that's some kind of brief background with like aviation and how it all links into air traffic management. I don't know if anyone has spotted any differences. Yes, this is a really interesting one. Someone says, talks about the engines and the thrust. And this was one of the really big issues for the Wright brothers. So in terms of the aerodynamics, they'd kind of worked that out pretty well. As Mike was saying, they wanted wings with a lot of lift. But one of the real issues that the Wright brothers had was getting that thrust. Basically, they couldn't get a big enough, strong enough engine to propel or produce that thrust. And so in the early years of aviation, between kind of 1903 all the way up until about the Second World War, so 1939, the big evolution in aircraft was actually the engine technology and producing more thrust. And then in 1943, that's where we moved from propeller aircraft through into kind of jet engines. And, you know, when we go on holiday, and on that picture there on the right hand side, that is a jet engine, whereas on the left hand side, that's a propeller. It's just sneaking round the kind of the back of the aircraft, and the jet engine can normally create a lot more thrust. And yet another difference is the kind of shape of the wings, and as you can see, the picture on the left hand side, so these are a lot more kind of boxed shape, and these wings are really good for kind of low speed aerodynamics. They've got what we would call a low aspect ratio, and that just basically describes the shape of the wings and basically means they're really good at creating a lot of lift when they're flying slowly. Whereas if you look at the aircraft on the right hand side, you can see they're a bit more slender, they're a bit more shaped. They are thinner at the tip of the wing, but where the wing is at the fuselage, basically the body of the aircraft, you can see that they are bigger. And again, that kind of all links into what we would call the aspect ratio. And it basically just means the aircraft is better and creates more lift, less drag, flying at high speeds. So some really good points there, all of them correct. So yeah, thank you for all of those points and pointing out all of those similarities and differences.
Lovely, thanks, Dan. And thanks again, as Dan mentioned, to everyone for your chat in the Menti there. Some great similarities and differences coming through. Hold that in mind for a bit later in the session as well. So now we're looking at what's happening now and going into the future, and we're going to take a look at using artificial intelligence. So for this part, we are going over to Lewis.
Thanks, Fiona. So I think maybe this relates to what Dan was saying about how over the last 100 years, planes have changed a lot. And the way we manage planes in the sky has also changed a lot. So Dan mentioned how we have a system of air traffic controllers now. So as the number of planes in the sky increases, they become increasingly difficult to manage. And there's so much data that we have to take into account when we're making those decisions. So across the same time period, we've made use of computers to make that easier. And the reason we've done that is because obviously there's so much data that we have to take into account. So it'd be very difficult for air traffic controllers and pilots to keep that straight in their heads. So they use computer systems to help them manage that. And as we go forward, we can make use of what's known as artificial intelligence to make that process even easier and more efficient. So what is artificial intelligence? Basically, it's when we can demonstrate human-like intelligence using machine. So what do I mean by intelligence? So intelligence can be many things. It could be being able to add numbers together, understanding language, interpreting images and video. So for example, a pilot in a plane might have to keep track of different wind speeds and that kind of thing and adjust their flight path accordingly. If a computer could do the same thing, we might say that the computer's exhibiting human level intelligence. So it might be useful just to describe how computers traditionally run and how that relates to artificial intelligence. So what I do as part of my job is I write instructions for computers that act on data. And those instructions are basically run from start to finish exactly as I've written them. So there's not really any intelligence being displayed by a computer in that case. It's basically just doing what I've told it from start to finish. And I wouldn't want to do anything else because I want it to be predictable. I want it to do exactly what I've said. So for example, an analogy for that might be if you've ever baked a cake, you need to gather your ingredients. You might need eggs, butter, flour, and milk. Then a stage in that recipe might be whisk the eggs, measure the flour, measure the butter, combine all the ingredients in a bowl. These are all instructions that you're having to follow as part of the recipe. And if you follow those instructions correctly, at the end, you should have a cake. The same is true with a computer program. I need to provide instructions exactly as required for the computer to carry out a program. But there's a different class of problem which is very difficult to describe, and that's what we use machine learning for. So what is machine learning? It's basically, instead of giving instructions to a computer and telling it exactly how to do something, we basically teach it how to do something instead. So we provide a lot of examples of data, what's called training data, and we basically just adjust our computer model until the data we give the computer results in the output that we want. So for example, if an alien came to Earth and they'd never seen a cat before, we might show them pictures of dogs and pictures of cats, and they probably wouldn't know the difference. However, if we kept correcting them every time they got it wrong, eventually that alien would probably be able to identify which pictures were dogs and which pictures were cats. The same is true with a computer with image recognition programs. We provide millions and millions, and I'm not exaggerating in that case, of examples of training data, and we just correct the model until we get the output that we want. So machine learning is, as I've just said, providing data and tailoring a model until we get an expected output. So how does that relate to artificial intelligence? Well, machine learning is one step in producing artificial intelligence. So it's a good way of basically providing solutions to problems that are hard for us to describe as instructions. And that could arguably allow computers to exhibit intelligence. So these systems are used in lots of different areas that you've probably come across. So if you've ever used Amazon Alexa or Siri by Apple, those systems are likely using machine learning for voice recognition. So if you ask your Alexa to do something, over time it's had to learn how to recognize, say, like an American accent or an English accent or say an Indian accent of someone asking Alexa to, like, what the weather's like today, or like asking them to Google something. When Alexa was released by Amazon, it'd probably be quite bad at recognizing speech. But over time, because there's so many people using the software, the people at Amazon can correct the model until Alexa is very good at recognizing speech. Another example, face recognition. If you've and photo tagging, if you've ever used Facebook or social media, computers are very good at like recognizing images that we take photos of and identifying what they are. Product recommendations as well. If you've ever done online shopping, when you buy one product, the recommendations might not be very good, but over time, the system will learn like what products you're likely to buy in the future, given what you've bought in the past. Video games as well. If you've ever played video games, you'll know that characters in the games can react to what you're doing as a player. That could learn in the same way, but also could be programmed by hand. So how does this relate to aviation? Well, the same principles could be applied to aviation in that we have so much data available to us. So we can leverage that by training models to help pilots and air traffic controllers to make smart decisions during their jobs.
Lovely. Liz, thank you so much for that. It just blows my mind the thought of using artificial intelligence with planes. So thank you for explaining all of that background as well for us. We are going to move on next to look at what you can do after this session to have some fun. We're going over to Yadola for this one.
Hi, yes. Thank you for joining our session today. If you like what you've seen and, if you're wondering what you can do next, perhaps you can make your own plane, paper plane, and test it. You can vary things, you can decorate it and test how far you can fly your plane, or how long it can stay in the air, and which one goes more straight than the other one wiggly. That sort of thing you can do, and also perhaps you can change it a bit, use different material, use I don't know, fold it differently, add a bit, take away a bit, and see the effect. Repeat your test. As Mike said, we're testing and we're learning more. But why not challenge your friends and family into this and make a competition and see, who wins in flying the furthest or straightest or keeps in the air for longest. But whatever you do, send us the pictures. We'd love to see it. And yeah, we will be sending some material for you, with folding instruction, and we are sending some folding instruction and after the sessions to aid you with your plane making. And in the meantime, have you got any question for us?
Brilliant. Thank you, Yadilla.
You are.
So I think I am right in saying that you can use YouTube chat to put your questions in there. If you want to know anything more about what we talked about today, or if you want to know about any of the jobs that we do, or Leidos, or anything at all like that, feel free to put your questions in. Either that YouTube chat, or we've got Menti back on the screen again. So thank you, team, for popping that up there. So the QR code is there, or you can go to menti.com and then just use the code 88511804. So again, we'll leave some time for questions to pop up there. Oh, we've got the first one in. First question, how are planes made? So any of our Leidos co-workers want to come on and answer that one?
Yes, that's a really interesting question. So I'll focus a little bit. So I said on Airbus, as I said, there's two main manufacturers in the world. So there's Airbus, which is focused more in Europe, and you've got Boeing, which is mainly a US company. And how they're made. So essentially for Airbus, they've got 4 or 5 big production lines, and making an aircraft is something that's really complicated. So each production line specializes in one particular part of the aircraft. So if we look here in the UK, Airbus has got a factory in a place called Broughton, which is just by Chester, which was the place where I grew up. And indeed, that's where I did my work experience. So when I was kind of 15 or 16 and had an opportunity to go and see their production line. And so you have all of the raw materials coming into the factory. So a lot of the aircraft traditionally were made out of a material called aluminium. The thing about aluminium is it's really strong, but it's lightweight. And then they would use techniques like riveting to join the various different pieces of metal together. And you'd have very specialized teams which would form and bond these parts together. And then you would, at the other end of the production line, you would have a series of complete wings. So that's what we do in the UK. And then they would all get put on a special transporter aircraft called the Beluga. And they would get flown over to a place in France called Toulouse. And that is what we call the final assembly plant. And so, as I said, in the UK, they make the wings. In various other parts of Europe, they make the fuselage. So that's the bit where we all sit in. They have the jet engines get made in another place. The various other elements of the aircraft all get brought to Toulouse, and that's where they then put all of these parts together. And then that's also where they do their test flying. So as Mike was saying, we need to test these things to make sure that when we all go on holiday or on business or whenever we need to fly, they all work as they should. But one thing that's really interesting over the last 10 to 15 years, there's been a move away from those traditional materials of aluminium, and we're using newer technologies, newer materials, the main one being carbon fiber or carbon composites. The thing about carbon fiber is that it's even stronger and even lighter than aluminium. So that's a really good advancement. And by making planes lighter and stronger, it really helps reduce the amount of fuel the aircraft are burning, which obviously helps with stuff like the environment and reducing our carbon footprint.
Fantastic. Thank you, Dan. Always amazes me how much you know about planes and flying. It's just a wealth of knowledge, so thank you. I can see we've got lots of questions popping in here now. So the next one we have down is, how do you make paper planes fly better? I don't know, Mike, if you want to come back in for this one. We had good chats, didn't we, about the paper planes we had in our experiment.
Sure, yeah, thanks, Fiona. Yeah, how do you make paper planes fly faster? Well, I think experimentation is a really kind of good kind of way to go. So, whatever you're trying, if it doesn't work that well, make small adjustments and kind of see if that improves things. And one kind of good bit of advice there is, if you are going to make adjustments, just make one at a time. Because if you make a number of adjustments at the same time and it makes it much better or much worse, you don't necessarily know which adjustment made it much better or made it much worse. So if you do just one at a time, that actually is a really good way to test it and understand exactly what the impact that your changes had. If it was me trying to learn how to make my airplane fly further or faster, I'd definitely do some Googling. Googling is your friend, and this is a truism of life and IT work as well, working in testing. Whatever question you've got, someone's probably asked it first on Google. So yeah, I would always just do a bit of research, and then take a fairly kind of structured approach to kind of refining your design. In my experience, and I've flown a few paper airplanes over the years, a couple of things you can do to improve it is actually adding weight to your airplane. And that's a little bit of an unintuitive suggestion, because the more weight you've got, you'd think that's going to make it, that's fighting against the thrust. But depending on where you position that weight, it can actually have quite a big impact on how well the airplane flies. So that would be one I'd maybe recommend kind of trying when you're kind of refining your airplanes. Maybe use a little bit of blue tack, a little bit of plasticine, and experiment with maybe putting a little bit at the nose of the plane. You might find that gives it a little bit more direction when you throw it. And you also might want to maybe experiment with, if you put a little weight on one wing but not the other, what does that do? And if you put a bit of weight on both wings, does that have a kind of counteracting effect? So these are all really cool things to kind of play around with and just kind of see what difference it makes, and then just kind of constantly kind of refining what your approach is. In the IT world, we call that iterating. We iterate through tests. So that's a good word, one of my favorite words, iteration.
Love so much education today. Thank you, Mike. I like the fact that everyone's obviously thinking about that competition as well with the paper planes and getting their tips in early. That question in the chat there about weight actually leads quite nicely on to the next question, which is, when did people start traveling on planes? So again, Dan, I thought you might pop up for this one.
No, so it's really interesting. One of the first uses of aircraft in a kind of what we would call a commercial sense, so flying not for fun but flying for kind of to make money, was mail. So kind of the Royal Mail here in the kind of UK, or the US Postal Service in America. So kind of in the 1910s, 1920s, that's where kind of was the first application really of the kind of aircraft. And then it was the kind of First World War and then the Second World War, where aircraft were used for moving troops kind of around the world. And then it was from there where then we have the kind of what's called the golden era of kind of aviation, the 1950s, the 1960s, the jet set era. So yeah, probably in between the kind of 1920s and 1930s is when we started to see kind of people using planes for human transportation. And then it really started to grow in popularities in the 1950s and 60s.
Fabulous. Thank you, Dan. And we've got a lovely time check here. We're nearly at time for the session, but maybe time for one more question here. And we can also, I'm sure, answer some more through YouTube, etc. afterwards if we didn't get to everybody's. Last question we can ask then, how do pilots know where to go when they're flying? That's a great question.
Yeah, really good. And again, this is another one that's kind of changed over time. So aircraft, the traditional way to fly aircraft is you would fly a heading. So I don't know if you have kind of are familiar with a compass. So that will tell you kind of where the north is. And then what you do, you'd get a map and you would work out where your destination was, and you would work out what heading you would need to fly at. So it could be a heading of 93 degrees, for example, and then you would work out how fast you're flying, and then you kind of work out how long it can take you. And again, kind of navigation, it was the Second World War which really drove an advanced our understanding in navigation. In terms of modern aircraft, that's still definitely something that aircraft utilize. But the main technologies that aircraft are moving towards are something called GPS, or Global Positioning Service. Also, that's an American system. You also got a Russian system called GLONASS, and you've got a European system whose name just escapes me. But essentially, these are many different satellites that are orbiting Earth. I believe there's about 30, 40, 50 satellites all orbiting the Earth, and basically the plane talks to these satellites and uses something called triangulation to work out specifically where it is. And it's exactly the same technology that you use on your phone, on Google Maps, on your sat nav. That's exactly the same technology that the aircraft are using.
Fascinating stuff. I'm learning loads here too. So thank you very much to Dan, Mike, Lewis and Udola for presenting with us on this session. Thank you everybody who's joined as well. Absolutely brilliant seeing your chat come through Menti and YouTube as well. Really appreciate you being with us on this session today. Feel free to check out Leidos on social media. You'll see lots of things there. We get lots of STEM involvement. So yeah, I'd say thank you so much for joining us today, and hopefully see you on another session soon. Bye.
Thanks all. Cheers, mate.
All right. Bye-bye.